what could possibly be better than us verifying the well-known formula that the area of a circle is pi r squared? We all know that, right? Area of a circle is pi r squared. Do y'all remember us verifying this earlier semester? I did it, but we had to use trig substitution to do it. So it was a little bit complicated when we did it. But everyone was like, I remember y'all cheered through, I think you threw dollar bills up here and stuff. Y'all don't remember it that way? Like, oh my gosh, we proved the formula. No? That's the way I remember it. Okay, that didn't happen. I'm sorry. What you're about to see is this is going to be just incredibly awesome how easy this problem is going to turn out to be. All right? So first, I'm using capital R. I don't know why, I just didn't want to use little r. Little r gets overused. So that's going to draw me a circle, correct? Radius capital R, but I would need my t to go from 0 to 2 pi for it to draw the whole circle, right? I'm only going to go on 0 pi. And the reason why is because I only need the top half of the circle. Don't I? And I'm going to try and find this area. Yeah? Whatever my answer is, I'm going to double it. All right, let's play the game. Integral from where to where? Alpha to beta, which is our restrictions on t, so 0 to pi. Next piece, g of t, right? What's g of t for us? R sine t. Okay, times, now the derivative of f. This is our f function, right? So the derivative of that is negative capital R sine t dt. Y'all agree with that? Okay. Factor out a negative r squared because r times r is r squared. And then all we're left with is sine squared t dt because we have sine times sine, right? And how do you deal with sine squared? Half angle identity or power reducing formula? This is going to turn into like a 1/2 and then something, then 1 minus something. Yeah, so we pull out the negative, we pull out the 1/2, and then we have 1 minus cosine 2t dt. I'm hoping that you recall this. I hope that your brain hasn't become so shut down that you can't power reduce something. That's okay? And now integrating these. This should integrate pretty clean, right? What's the antiderivative of 1? T, right? Because we're integrating with respect to t, so be careful. Don't put x or something like that. So that line becomes negative 1/2 capital R squared. I'm now doing the antiderivative, so I don't need the integral sign anymore. T. Now, what's the antiderivative of this thing right here? Minus 1/2 sine 2t. And then we're going to evaluate this integral 0 and pi. And when we plug in pi, what do we get? So pi goes in first. That's going to be pi, right? What is sine of 2 pi? 0. So this whole term's gone, right? So all you have is a pi out here, and you've got that out front. So negative 1/2 capital R squared times pi minus, now we plug in 0. When we plug in 0, sine of 0, 0, 0. That whole thing zeroes out. Times that, still 0, so we get that. And we're getting a strange answer. Yeah, it's negative, right? And that might initially bother us. But we had negative areas before. When we first studied areas under curves, do you remember when we did the sine curve? And we said that if you go from 0 to pi, you get 1. And it was weird. I was like, that's strange that that's 1. That area is 1, but if we go from 0 to 2 pi, we got 0. It's because these canceled each other out, which meant this area down here was counted as negative. And I tried to explain that the reason why was because when you measure the height of your rectangles for your sum, your Riemann sums, those heights were negative because your function's negative there. So it kind of made sense, right? Here, the reason why we're getting a negative answer has nothing to do with the fact that we're above or below the x-axis. Nothing to do with that. What it has to do with is the direction we're moving as we're integrating. We're actually moving 0 to pi. Remember t, you can't see t, right? You can't see t in the picture. We're actually moving, we're sweeping through like this when we're creating the area. It's from right to left. And so your dx is actually moving that way instead of this way. So it becomes negative. But that's okay, so we're just going to look at the area as an absolute value. So if we just absolute value this thing, then that gives us the area of half. Half of the area of a circle is 1/2 pi r squared, so double that answer, you get pi r squared. Done. No trig sub.
Pi to 0.
Could you have gone what?
Could you have gone the other way?
Oh, pi to 0, just flipped it? Yeah, remember what happens, but you wouldn't have really known to do that, right? Until you got this answer and then you said, oh great, it's off. So yeah, if we switch the order of integration like that, then it always just changes the sign. All right, that was pretty cool. We didn't even need, all we needed was a little bit of pre-cal and how to take the antiderivative of cosine 2t, and other than that, it was pretty straightforward. Do you agree that was pretty straightforward? I hope I'm not making assumptions here. Okay. All right, moving along. What about arc length? We should be able to find the lengths of curves. So if you recall, the way we came up with that formula, that first one, is I had drawn a curve. I said we're going to kind of zoom in, imagine approximating that curve with a straight line segment, creating a right triangle, and saying like this was kind of like dy, and this was like dx, and that means the hypotenuse here would be the square root of dx squared plus dy squared. That's very roughly speaking. You could go back in the lecture when I actually came up with this formula, that first one, because I did show you where that formula came from. Using that same concept, we can do the same thing, but see the difference is our dx is not going to turn into a 1. In the previous formula, this right here turned out to be dx, which was 1. The derivative of x with respect to itself would be 1. But now, because x and y depend on t, the derivative of this is not 1. It's just dx dt. But do you see how similar the formulas are? Yeah? So that's the one we'll use. And we're going to do another example. This one's going to just blow your mind. $5 bills are going to rain down on me. No, it's not going to be that. What's the circumference of a circle? 2 pi r. Let's verify that. So I'm going to take that same function, y equals r cosine t, x equals r cosine t, y equals r sine t. This time I'm going from 0 to 2 pi, going all the way around. Okay? So I'm going to say that the length of this should be the integral from 0 to 2 pi, square root, and now according to that formula, I need the derivative of x with respect to t, but then square, don't I? What is the derivative of x with respect to t? So that's this right here. With respect to t would be negative r sine t, but then I'm going to have to square it, right? So this is going to be r squared sine squared t. I'm also going to need in my formula dy dt squared. So take your y function and take its derivative, which would be r cosine t, and square it, which should give you r squared cosine squared t, right? And just plug in. So right here goes r squared sine squared t plus this one, r squared cosine squared t dt. And that may look ugly, but do you see what happens? R squared factors out from both. So when r squared comes out of both of these, I can then take it out of the root, and it becomes an r on the outside of the root. And I'm going to take that out of the integral completely. 0 to pi. What's still underneath that root when I take that r squared out? Sine squared t plus cosine squared t, right? Which is really just 1. That's your major Pythagorean identity from pre-cal. So this is just square root of 1. Square root of 1 is 1. So I forgot 2 pi up here. That was 2 pi right there. 0 to pi of 1 dt. We're ready for an antiderivative. What's the antiderivative of 1? T. So this is just capital R times t evaluated 0 to 2 pi. Plug in 2 pi for t, and what do you get? 2 pi r. Plug in 0, what do you get? 0. Your answer is 2 pi r. It's pretty awesome. So in the homework assignment, they're just, I'm going to have you, the book's going to give you some parametric equations, right, for x and y. Going to ask you for some derivatives. When is the slope of the tangent line horizontal? When is it vertical? It's things that we've done, right? Find an area, do an arc length. So just apply the formulas. That's all you have to do. How do you all feel about this? Like series, chapter 9 so far down here? Yes. It should feel like it's down here compared to the chapter 8 stuff. All right. Awesome, awesome. Pretty sure that's the end of those notes, isn't it? Okay. Moving on to 9.3. We're just going to get to the beginning of this. We won't get through it all. It's what? It's going by fast because it's so much fun. You're having fun. That's what it is. How many of you have heard of polar coordinates before? Physics? Okay. So look, I'm going to give you kind of an introduction to polar coordinates the best way I can make it make sense. My 7-year-old daughter came home with a math homework problem the other day, where it had like this real rough graph like this, and it had like pictures, cute little pictures of people in inner tubes on a river. And it was like dad, mom, like sister, brother, and then it was all like gridded out, like you could see these grids, and it was asking, like, dad was right here, and this was like 2, and this was like 2. There's the origin. So it was asking, like, where's dad? Like, at what point is dad, right? And so her answer was, 2, 2, right? So since childhood, we've had this idea of points being on what we call the Cartesian plane. This is called the Cartesian coordinate system. And Cartesian. I think that's it. I want to say my spelling's off there. I know, but let me see. What did I do here? Oh, I put too many I's. Oops. Cartesian. So if you were trying to explain to somebody what Cartesian was, if they'd never seen it before, here's one way you could do this. You could say Cartesian in 2-dimensional space on a flat sheet of paper works as follows. You draw 2 perpendicular lines, right? We call this point right here in the center the origin. And that can be represented with this ordered pair 0, 0. Then, if you pick another point on this flat sheet, anywhere you want, x, y, then this number x is the distance you should travel along this axis, right? The y is the distance you should travel. How would I say that? So, trying to get you to think about this. Imagine I'm this person standing here, right? Like this. This is my head, my feet are on the ground. So here I am. Okay, I'm standing at the origin. If someone's trying to explain Cartesian to me, the first thing they need to tell me is which way I need to start in terms of facing. Which way should I face? Down this x-axis, right? Then from there, the directions of where to go are given to me by this point. So if it says on that point, 3, -2, then what I'm going to do is this. Standing at the origin, I'm going to walk out 1, 2, 3, stop, right? And then what? I'm going to turn perpendicular, okay? So now what I've done is I've walked out 1, 2, 3, and I've turned this way, right? And I'm pointing in that direction. And then walk which way? Backwards 2 spots. And that's going to put me down here, right? That's the standard practice. This x-coordinate tells you which way to walk in this direction, then turn 90 degrees, and then walk this number, either forward or backward. Yes? That's how we get around Cartesian. But that's not the only way you could give someone directions to get to that point. What's another way that I could get from here to you? I could walk out 1, 2, 3, 4, 5, right? Turn, and then 1, 2, whatever to get to you, right? That's one way. Another way would be what? Instead of telling me how far to go that way and that way, you can just tell me how much to turn and then how far to walk, right? That's polar coordinates. It still requires 2 pieces of information. Just like Cartesian requires 2 pieces of information, polar still requires 2. An angle that I turn and a radius I walk. So if I instead connect the point down to the origin, I call that r, and the angle that I form between that line segment and the x-axis, theta, then polar coordinates is still an ordered pair, but instead of x and y, it's the r and the theta. Pardon me? On a different what? Okay. It's just another way to walk around your flat universe, okay? You've got this flat universe you're living in, and you want to move around in that universe. You can do it different ways. Cartesian's the standard way, but polar is another way. When you get to 3-dimensional space, there's Cartesian, there's spherical, there's cylindrical coordinates. So there's 3 standard systems we use in 3-dimensional space. There's 2 that we use in 2-dimensional space. But there's more. There are others, you know. All right, so let's try and find some relationships between Cartesian and polar. Well, the most standard relationship that we could create is using that right triangle again. So we know that we will always have this identity, right? This will always be true. That's guaranteed by the Pythagorean identity. We have some other relationships. We actually know how to get theta. We can get theta by using the inverse tangent function. If I know what y is, and I know what x is, I know tangent of theta is y over x, right? So tan theta is y over x. So if I take arctan on both sides, then theta would be arctan of y over x, right? That's another relationship we have, so long as x isn't 0. If x is 0, that's not defined. Other relationships we have, x is r cosine theta, right? And y is r sine theta. That's just using our trig functions on this like we did earlier. And from this, we have everything we need to be able to convert from one coordinate system to the other. So that's what we're going to practice doing now. We're going to use these identities, and I'm going to give you a Cartesian point and ask you to convert it to polar. And then I'm going to give you a polar point and ask you to convert it to Cartesian. So what's that first point I give you? -5, oops, wrong one. -5, 4. Okay, so this is a Cartesian point. -5, 4. I want to convert this to polar. That means I want it to be turned into an r and a theta. Do you think the order matters here in polar? Like, you know how x and y it matters? Like if you flip these, it's not the same point? Polar, do you think it matters? Absolutely, it's still an ordered pair. We always do r first, then theta. It's always r, then theta. It's never theta, then r. Okay?
What would be different?
Pardon?
What would be different? Which is how we do it.
What do you mean? It's the standard practice. I mean, that's just the accepted order. But, I mean, these would mean two different things. If I said radius 3, angle pi over 4, that would mean turn pi over 4 and walk out 3. But if you write pi over 4 and then 3, that means turn by 3 radians and walk out pi over 4. Pi over 4 is some number, right? So that would be completely different. Make sense? Okay, so now let's do this. How can we get r? So it's on your notes. I have an equation for r. Square root of the x squared plus y squared. So r is the square root of x squared plus y squared. That's just the Pythagorean identity taking the root of both sides. And then for us that would be square root of -5 squared plus 4 squared should be root 25 plus 16 root 41, which is approximately as a decimal like 6 point, anyone get that yet? 6.5? 6.4 something? Okay. Good enough. About 6.4. All right, let's get theta. Theta would be arctangent, so you have to use your calculator for this, unless you know what arctangent of 4 over -5 is, in which case you probably shouldn't be in this class, if you can do that in your head. What are you getting? -0.67. Now you're in radian mode, right, on your calculator? Yes? So I'm going to put radians here. You don't have to put radians. It's understood that it's radians. I'm just putting radians to remind you. Now, if you had been in degree mode on your calculator, what would you have gotten? -38.65. Now, when you write something like this, you have to put the degree symbol or else it is incorrect. If you put -38.65 without the degree symbol, then that means -38.65 radians, which isn't the same. Okay, so we ready to write the point down? R theta. What's R? Yeah, I'm going to do root 41. Is that okay? I could do 6.4. And then the angle -38.650. Like this? Yeah? This is wrong. What's wrong? How do you mean? Yeah, this has something to do with our arctangent function. Remember, arctangent has a domain restriction? It's only going to spit back answers between two things, -π/2 and π/2. It's never going to spit back any angles that are outside of quadrant 1 or 4. But look at our point. Where's our point? If we graph it, where is it? 1, 2, 3, 4, 5, right? -5 and then up 4, 1, 2, 3, 4. So there's our point. Look at our answer. It doesn't make any sense. We're supposed to stand here, face out the x-axis, and rotate by how much? Negative 38 degrees, which would put me like somewhere around here, and then walk out how far? Square root of 41, which I would be like somewhere out here, right? It's wrong. So, do you think that that answer has anything to do with the right answer? Yes. This angle is, it does lie on a straight line with that one. So what are you going to have to do to get the actual real angle? Add 180 to this. Add 180 to this. I gave you your first example as a tricky one because I want you to be ready. Just my advice to you when you're doing this conversion is to just draw the point first, and then when you get your answer, see if it makes any sense. Like if this doesn't take you to that point, then make any adjustment you need to make. Now I could do this. Does anyone know a way I could fix this real easily without changing my answer? Is there something that you could think of that I could do here that would be kind of clever? I could make it in a negative 41, root 41. Because then I would do what? Rotate out negative 38 degrees and then walk backwards. But we don't normally like to make the radius negative. It's possible, but we don't normally like to do it. So instead, just add 180 to this. Okay, so scratch that. What is that plus 180? Like 141 point.
You're adding 180, right?
Huh? Do what? I'm adding 180 to that?
41. It's a negative.
It's a negative though.
Oh.
Right? Is that right? Pretty sure that's right. Okay, so are we satisfied that we would rotate 141.35 degrees and then walk out 6 point something? That should put us there. All right, what about the other way around? What if I gave you a polar point and ask you for it in Cartesian? This one, the good news, you don't have to worry about that arctangent function coming and biting you, okay? This one is just, you just plug it in, okay? So this is 7 pi over 6. That's r, that's theta, right? And I want to go to xy. So to convert, x is going to be r cosine theta, so 3 cosine of 7 pi over 6. And then the y is 3, and then sine of 7 pi over 6. And 7 pi over 6, let's see, that's on our unit circle, that's right here. That's the point, negative root 3 over 2, 1/2, negative 1/2. That's that point. So cosine is the x-coordinate off this. So we should be getting 3 times negative root 3 over 2. And then here, 3 times negative 1/2. I could go to a decimal here, but I'm going to leave it exact. There you go. That's it. Yeah, that one's a lot easier because you don't have any problems because you're not using any inverse functions. Inverse functions cause problems because of domain restrictions. This is the same as this, right? Now there's obviously a downside here. Does anyone kind of have like notice what the downside is of these two systems? Like if I just wrote this on the board right now, okay, let me erase everything. All right, and I say plot 3, 5. My daughter's going to plot that in Cartesian, right? But you don't know what system that is. Technically, you don't, right? Most of the time, we understand that that's Cartesian. But there's no notation that we use to distinguish the two. We don't like, it'd be nice if maybe we said, okay, because this is, I want you to think this is a polar, I put a little p down there to let you know it's polar, or a little c if it's Cartesian. We don't have any notation like that for that. So you have to understand it within the context of the problem you're working in. Like, what system are you in? Okay? Did I show you this one earlier this semester? Hold on. Let me see. Oh, shoot. I don't know if I'm going to be able, I think, hold on. Yeah, have I shown you all this? Did I show you all that?
Yeah.
That's true. This is true. If you look at this as a decimal expansion in binary, the decimal, this 0.11 forever in binary is equivalent to this in base 10. But there's no way you would have known that by me writing it, right? You would assume I'm in base 10 on both of these. You could, yes. But even there, we do have something, right? With polar Cartesian, there's no nice thing we use. Okay? All right, we are almost out of time, and I'm just going to show you one last little thing, and then we're going to wrap it up, and then we'll come back. We'll knock out the rest of this next class. What would, if I were to tell you that r is always 3, give you an example of these curves. No, you know what? I'll skip that. I'm going to not do that till next class. If you go online right now and you print and you go and Google like graph paper, like have you ever had to print out your own little like graph paper online? Okay, so you can like get graph paper, and when you print out graph paper, it's going to print like an x and y axes, and then it's going to have like a real faint, you know, like grid lines, and that's to help you, isn't it? Graph things. Okay. And obviously this graph paper is Cartesian graph paper. So what they've done is they've said, all right, we're going to take the idea of x and y here. All these vertical lines represent this x being held constant. So like if x is 0, I'm here, right? If x is 1, I'm here. x2, x3, x4, right? The horizontal lines are holding the y constant. Y is 0, y is 1, y is 2, y is 3, right? -1, -1, 2, 3. Well, there's actually polar graph paper. And it looks like this. What they do is first they say, all right, let's hold the r's constant. What would all the points look like that have a fixed radius of 0? That would just be this, right? How about all the points that would have a fixed radius of 1? It would be a circle. Radius 1. Then they would say, how about radius is 2? Then 3. Right? And so you have these concentric circles. Yeah? Then they say, what would happen if we held theta to be constant? Now with theta, since that's an angle, we like to use the standard angles, the ones that we're most familiar with, like 30 degrees, 45 degrees, 60 degrees. So what they would say is, what do all the points look like that have theta as, let's say, pi over 4? Wouldn't that be any point that lies on that line would have a theta of pi over 4? How about pi over 6? Would be any point that lies on that line. And then pi over 3, 60 degrees. And they do this for each of these quadrants. So like this. Get the idea? So now if you want to graph like, 3, 5 pi over 4, you would just go out 3, 1, 2, 3, and then go to 5 pi over 4, which would take you here. See how polar graph paper would work? Just know it's out there. We're going to wrap it up. We will come back and continue. Yeah, any questions?
You're like really good lines,
You like those circles and
though.
lines?
Good lines, yeah.
You don't like my circles, just my lines? Somebody taught me something one time to draw a circle, a big circle on a board. They said you take, because I'm left-handed, they say you take your off hand, your other hand, and then you draw backwards. Like this. I don't know. It's a quick circle, but it's a pretty good quick circle. I mean, I'm sure I could take my time and draw a better circle, but if you want a quick circle, I don't know, it's weird. It works out. I have no idea how that works. I don't know. It's weird.